What specific problem does the proposed method aim to solve in the context of language models trained on the next token prediction objective?
The proposed method aims to solve the problem of non-identifiability in language models trained on the next token prediction objective. Specifically, the paper discusses how different models can be indistinguishable by likelihood, even with infinite data, due to non-identifiability. The study highlights the limitations of statistical generalization in understanding language models in the saturation regime, where models achieve near-zero training and test loss. The paper argues that studying inductive biases in this regime is crucial for understanding properties such as rule extrapolation, implicit in context learning, and parameter non-identifiability. By focusing on non-identifiability and inductive biases, the method aims to uncover additional properties of language models beyond statistical generalization, such as rule extrapolation abilities and transfer performance.
How does the proposed method work, and what are the three important notions of non-identifiability discussed in the paper? Illustrate step by step.
The proposed method in the paper focuses on studying language models in the saturation regime, where they achieve perfect statistical generalization, but may not exhibit practical model properties, such as out-of-distribution generalization and transferability. The paper argues for understanding inductive biases that go beyond statistical generalization to explain these phenomena. The three important notions of non-identifiability discussed in the paper are: 1. Functional non-identifiability. This occurs when the collection of conditional distributions in probabilistic models is not uniquely determined by the joint distributions they define. It is guaranteed only when all finite prefixes occur with non-zero probability. Otherwise, models that differ in completing zero probability prefixes are indistinguishable by the Kullback-Leibler divergence, KL divergence. 2. Epsilon non-identifiability. This concept relaxes the notion of functional non-identifiability by positing that there exist properties of models that other models very close to them do not possess within a certain epsilon threshold in terms of KL divergence. This means that even though a unique global minimum exists, there are near minima that differ in important ways. 3. Parameter non-identifiability. This notion states that functionally equivalent models can be described by different sets of parameters. While this does not affect the model's zero-shot test performance, it can significantly impact transfer learning and fine-tuning processes. This concept highlights the importance of understanding how different parametrizations can lead to varied behaviors during fine-tuning and transfer tasks.
What are the theoretical or practical benefits of studying language models in the saturation regime as proposed in the paper?
Studying language models in the saturation regime, as proposed in the paper, offers both theoretical and practical benefits. The theoretical benefits include understanding the inductive biases responsible for good generalization beyond statistical measures. By focusing on the saturation regime where models achieve near-zero training and test loss, researchers can uncover the inductive biases that lead to beneficial qualities not explained by statistical generalization. This approach allows for a deeper exploration of model behavior and properties that go beyond traditional statistical measures. Additionally, studying language models in the saturation regime provides insights into non-identifiability, highlighting the limitations of statistical generalization and the importance of considering practical model properties. From a practical standpoint, investigating language models in the saturation regime can lead to improved generalization measures tailored to the properties of natural languages. By developing alternative metrics such as compositional, systematic, and symbolic generalization, researchers can better evaluate model performance on out-of-distribution data and transfer tasks. This can enhance the understanding of how language models learn and generalize, especially in complex tasks like reasoning and symbolic manipulation. Furthermore, Studying inductive biases in the saturation regime can help identify qualitative model properties that influence model behavior during fine-tuning and transfer learning. This can guide the development of more effective training strategies and model architectures for language models, ultimately improving their performance on diverse tasks and datasets.
How is the non-identifiability of less than AR greater than probabilistic language models showcased through the 3 case studies presented in the paper?
The non-identifiability of less than AR greater than probabilistic language models is showcased through the 3 case studies presented in the paper by highlighting different aspects of non-identifiability in less than AR greater than LLM greater than. 1. Case study: non-identifiability of rule extrapolation. This case study demonstrates functional non-identifiability, where models are indistinguishable by the likelihood when certain prefixes have 0 probability under the distribution. It shows that completion distributions for certain prompts are non-identifiable, leading to different behaviors in completing prompts that break specific rules. This highlights how non-identifiability affects the model's ability to generalize and extrapolate rules beyond the training data. 2. Case study: non-identifiability and less than ICL greater than. This case study introduces the concept of epsilon non-identifiability, where models close in KL divergence may exhibit different properties. It shows that even models fitting the pre-training distribution closely in KL divergence may not exhibit less than ICL greater than. This demonstrates how near-equivalent models can behave differently on low probability sequences, emphasizing the importance of considering non-identifiability in understanding model behavior. 3. Case study: parameter non-identifiability and fine-tuning. This case study focuses on parameter non-identifiability, where functionally equivalent models can behave differently during fine-tuning and transfer. It illustrates how different architectural constraints and optimization methods interact with the model's parameters, leading to varied performance after fine-tuning. This case study emphasizes the impact of parameter non-identifiability on model behavior and performance in downstream tasks. Overall, these case studies provide concrete examples of how non-identifiability manifests in less than AR greater than probabilistic language models, showcasing the complexities and challenges in understanding and predicting model behavior, generalization, and performance on downstream tasks.
What results were achieved in the empirical demonstration of zero-shot rule extrapolation with a decoder-only transformer as mentioned in the paper?
In the empirical demonstration of zero-shot rule extrapolation with a decoder-only transformer as mentioned in the paper, it was found that the model developed an ability to extrapolate the rule in 43.7% of the cases. This ability to extrapolate the rule was observed even though the loss function used during training was agnostic to this behavior. Additionally, when 2 additional models were trained in an adversarial and an oracle setting, all 3 models reached the same minimal test loss, but displayed widely varying rule extrapolation performance. This variability in rule extrapolation performance among models with the same minimal test loss highlighted the presence of additional inductive biases influencing the behavior of the models.
What future research directions are suggested in the paper to enhance the understanding of inductive biases and the saturation regime in language models?
The paper suggests several future research directions to enhance the understanding of inductive biases and the saturation regime in language models. Firstly, it advocates for studying inductive biases that are not problem or loss specific, focusing on qualitative characteristics that enable reasoning about performance on new tasks and alternative generalization measures. Secondly, the paper highlights the importance of intertwining statistical generalization with language model (LLM) relevant inductive biases to better understand phenomena such as extrapolation performance. Thirdly, the paper encourages investigations into qualitative model properties, such as sparsity, which can arise from inductive biases alone and impact the behavior of deep neural networks. Additionally, insights from algorithmic information theory, specifically connecting model properties to the Kolmogorov complexity of generated text, are suggested as a promising direction for understanding LLMs and building general-purpose models. Furthermore, the paper proposes using formal languages, such as probabilistic context, free grammars, PCFGs, as testbeds to study compositionality and other language properties in LLMs. Lastly, insights from the transformer architecture, particularly using computational models like RASP, are recommended for characterizing the algorithms implemented by LLMs and developing novel complexity metrics specific to LLMs.